What's up, everybody, and welcome back to another video from the Scalar Learning channel on the digital SAT math. This is a video that is so important, so critical. It's going to be so helpful for everybody studying and preparing for the digital SAT. And this is the digital SAT math formula Bible. It's got all the critical concepts and formulas that you need to be successful on the digital SAT. And by the way, if you guys are looking for the best resource on planet Earth to study for the digital SAT, you got to check out the SAT crash course. The link is in the description below. And if you use the code SCALAR, you'll get 20% off. Not only do they have 10 practice digital SATs, they also have my video solutions to each and every math problem on those practice tests. So you can make sure that you understand everything when you walk in on test day. Without further ado, let's do it. All right, so starting off with item 0, right? Everything's numbered, and this is item 0, and there's a reason for that because this is actually just referencing all of the given formulas. This is the reference sheet that is accessible during and throughout both math portions, Module 1 and Module 2 of the digital SAT. So you can pull this up anytime, and all these formulas here, it's got area and circumference of a circle, it's got conversions between radians and degrees, right? It's showing you right here that 360 degrees is equal to 2 pi radians, and it's telling you that the sum of angles in a triangle is 180 degrees, all these great volume formulas, and even special right triangles. So a lot of these formulas I'm not including in this digital SAT math formula Bible, with the exception of special right triangles and Pythagorean Theorem, just because they're so important. So I'm going to reiterate those, but the rest of these are not there for a reason because you can find them right here. So get familiar with these formulas, get familiar with how to pull them up so you can use them in the best way possible. So formula number 1 is how to calculate slope of a line when given two coordinates. So let's check it out, right? It's m equals y2 minus y1 over x2 minus x1. And here's an example, right? Let's say we got coordinates 7, 2, 5, 1. And by the way, how you label x2 and y2, x1 and y1 is arbitrary. Just make sure you stay consistent with the subtraction. Now we're going to subtract, and in this format, we're going to go top minus bottom, right? So we've got 2 minus 1 on the top, the difference of the y's, over 7 minus 5 on the bottom, the difference of the x's, and that leaves us with 1 over 2, and that's your final answer for the slope. Boom, done. Formula number 2 is slope-intercept form for a linear equation. This is super important, and that is y equals mx plus b, where m is the slope of a line, b is the y-intercept. So just so you can see a quick example, we got y equals 2x plus 7. We got a slope of 2 and a y-intercept of 7. Now, if we looked at this on a graph, it would look like this. There's our nice y-intercept right at 7. That's where it hits the y-axis, and the slope is 2, which can also be rewritten as 2 over 1. So that's a rise of 2 and a run of 1, meaning a horizontal distance of 1. So that's how you do it. Next, we got point slope form. This is also super important. Y minus y1 equals m, which is the slope, times x minus x1. So again, m is our slope. And x1 and y1, what is that? Those are just values. It's one point, any point on a line. You can plug that in and you'll get a nice equation of the line. So here we have an example. We have y minus 4 equals 3 halves times x minus 3. So the slope, of course, is 3 halves, and the coordinate would be 3 comma 4. So if we look at the graph here, you can see there's 3, 4 right there on the graph, and then we got that rise of 3 and a run of 2. That's how you do it. Done. Formula number 4 is how to find the midpoint of 2 points, okay? So what you're basically doing is you're taking the average of the x values of the 2 points, the average of the y values of the 2 points, and you got it. And that makes a lot of sense because midpoint is in the middle. You find that by taking the average. So for example, right, if we've got this as our formula, if we take the points 8, 4, 6, 7, I'm going to take the average of 8 and 6. I'm going to take the average of 4 and 7. So that's going to be 14 over 2, which is 7, 11 over 2, 11 halves, or 5.5. Next, we get to the distance formula. So this isn't used a ton necessarily, but a lot of times it's really helpful, especially if you're trying to calculate the radius of a circle and you're given the center of the circle and a point on the exterior of the circle. So here we go. Here's the distance formula. Distance equals the difference of the x value squared plus the difference of the y value squared and, the square root of that. So let's check it out here. If we have 2 points, for example, right, 5, 3, and 1, 0, if we want to find the distance between these two, plug and chug, right? 5 minus 1 squared plus 3 minus 0 squared. 5 minus 1 is 4. 4 squared is 16. Plus 3 minus 0, that's 3. Squared is 9. So we got 16 plus 9 is 25. And the square root of 25 is 5. So that's how you do it. Done. Next, we got length of an arc, okay? And what's an arc? We're talking about on a circle. It's like the little crust. It's a piece of the circumference. Hence the formula, right? This makes a lot of sense. It's n over 360. N is the central angle that cuts out this arc times 2 pi r. Now, you'll remember 2 pi r is the circumference of a circle. So we're taking a piece of that circumference, right? So if we look at this graph, it makes a lot of sense. Again, it's that crust of the pizza. N is that central angle, r is the radius. That's how you do it. Next, we're going to come to area of a sector, which is very similar to the length of an arc, right? We have a similar formula, and now we're taking the central angle n over 360, and instead of multiplying it by 2 pi r, which is the circumference, we multiply it by the area of a circle, which is pi r squared. So if we look at the graph, now the sector, it's like the full slice of the pizza, right? N over 360 times pi r squared, boom, done. Next, we're on to the quadratic formula, very important for solving quadratic equations. The formula is negative b plus or minus b squared, square root of b squared minus 4ac all over 2a. And this is used when you get a quadratic in standard form. So for example, when it's in ax squared plus bx plus c, you plug this in and it's going to give you the value of the x-intercepts. Moreover, if this ever equals 0, you know that when you use the quadratic formula, you're going to get the actual solutions, the values of x. Next, we're on to SOHCAHTOA. This is very important for trigonometry, okay? This is the most important acronym, and it stands for sine is equal to opposite over hypotenuse. And notice that's sine of A, so it depends which angle we're talking about. But sine of A is equal to the opposite leg divided by the hypotenuse. Cosine is equal to adjacent over hypotenuse. Notice the color coding. And last but not least, tangent is equal to opposite over adjacent. And a very important thing to remember is when you have similar triangles, meaning the triangles have the same angles and proportionate side lengths, sine of corresponding angles in the different similar triangles are always going to be equal. Next, we're on to probability, which is the number of favorable outcomes over the total number of outcomes. So we can quickly say, right, if you're playing a game and there's 10 different outcomes, and there's 3 of those outcomes that cause you to win, your odds of winning are 3 out of 10. That's basically the gist of probability. Next, we're on to the circle equation. Very, very important. They love to ask questions about circles and the circle equation on the coordinate plane. So check this out. It's x minus h squared plus y minus k squared equals r squared, where if we look at this circle, h comma k is the center of the circle and r is the length of the radius. So if we look at it in an example here, right, x minus 2 squared plus y plus 5 squared equals 36. The center is going to be positive 2, negative 5. Again, we're taking the opposites of those values. And the radius is the square root of 36, which is 6. Next, we're on to exponential growth, okay? So this is our general formula, y equals a, which is our initial value, times 1 plus or minus r to the t power. Again, there's our initial value, what we're starting with. R is your growth rate, and t is your time, okay? And it's plus or minus because this can represent both growth and decay. So when we're talking about exponential growth, here's an example. We have initial value of 200. We're growing at 13% per year, and we want to know what is it going to grow to in 3 years. So we plug and chug, but again, percentages we enter in decimal format, so it's 0.13. That's how you plug and chug. Now, if we have exponential decay, it's very similar, right? We have an initial value. Now we have a decay rate. It's decreasing at 9% per year, and our time is 2 years here, right? So instead of adding that 9%, we're simply subtracting it, aka what's going to be inside at the end of this is going to be 0.91. That's how you do it. Done. Next, we're going to talk about the formula to find the vertex of a parabola when we are in standard form. Again, there's standard form, y equals ax squared plus bx plus c. Now, how do we get the vertex? It's simple. X equals negative b over 2a. Now, this gives you the x value of the vertex. To find the corresponding y value of the vertex, you take that value and just plug it back into the equation. Number 14 is vertex form of a parabola. Okay, you need to recognize this. So this is, again, standard form down here at the bottom, and this is vertex form. Okay, when it's in this form, it's really cool because you can tell what the vertex of this parabola is, right? And the vertex is going to be h comma k. Notice it's x minus h, so we're taking the opposite of that value, right? You might think it's a negative, but we flip it, and the k we leave alone. We don't flip. So that's how you do it. Next, we're on to the Pythagorean Theorem. Again, that's on the reference sheet, but we're going to state it again because it's so important. This is a squared plus b squared equals c squared, and that's true for any right triangle. Okay, so here's a right triangle. We've got a and b, which are the legs, and it doesn't matter which is which, right? B doesn't have to be longer. It doesn't have to be shorter. It doesn't matter. But the key is that c must be that hypotenuse, meaning the longest side opposite the 90-degree angle. Next, we're on to 16 special right triangles. Again, this is on the reference sheet, so you don't have to memorize these, but I wanted to show you them because they're very, very important. And we have two special right triangles, a 45, 45, 90. Notice you have two 45-degree angles and a 90-degree angle. And then we have and by the way, for this one, the side lengths, the legs are both the same. They're both equal, so we call them x and x. And then whatever those legs are, the hypotenuse is those legs times radical 2. So it's x times the square root of 2. Now, if you're given the hypotenuse and you need to find the legs, you should, of course, divide by rad 2. We also have a 30, 60, 90 right triangle, right? Where we got the 90 degrees and a 30 and a 60. Now, in this case, the smallest side is x. Then we go to the leg, the bigger leg, and that's just the smaller side times radical 3. And then the hypotenuse is double the smaller leg. Now, if you're ever trying to figure out all three sides or an additional unknown side, make sure no matter what side you're given to start with, you find the smallest side first. So, for example, if you're given the hypotenuse and you're trying to find the long leg, divide by 2, find the little leg, then multiply by rad 3 to get the long leg. Next, we got this nice little formula, and you might say distance equals rate times time. That's pretty simple, but I think it's a very important formula to keep in mind of, especially for rate problems, okay? So distance equals rate times time. Rate is also kind of synonymous with speed, and make sure that the units of the rate are the same as time. So for example, if you've got miles per hour and then they give you time in minutes, you need to convert that time to hours. Next, we're going to talk about a relationship between sine and cosine that is tested very frequently on the SAT, which is that sine of an angle equals cosine of the complement of that angle. So what do I mean? I mean that sine of 10 equals cosine of 80, because 10 and 80 add to 90. That's the definition of complementary angles. Furthermore, sine of 20 equals cosine of 70, sine of 30 equals cosine of 60, and so on and so forth, right? We have all these relationships. So just remember that because it's tested a lot. Next, we are going to go over the sum of solutions of a quadratic. Again, this is a nifty formula because it's tested a lot. So if they say, hey, we got this quadratic, what are the sum of the solutions? So it's not like find a solution or find both solutions. We want the sum of the solutions. Of course, you can find the individual solutions and add them together. But this is a nifty little shortcut. It's simply negative b over a. That's how you do it. So for example, if we have this equation, the sum of the solutions would be negative 7 over positive 2. Boom, done. Another one that is now being tested more frequently on the digital SAT is the product of solutions of a quadratic. So similar to the sum of solutions, right? If we have our standard form here, it's going to be c over a. Now in this example here, 2x squared plus 7x minus 5. Again, c is going to be negative 5 and a is still 2. So the product of our solutions would be negative 5 over 2. Now we're talking about the discriminant, again, of a quadratic. What is the discriminant? It's the part of the quadratic formula under the radical. And if we have a nice quadratic like this, it is b squared minus 4ac. And this tells us a lot about the nature of the solutions of a quadratic equation like we see here. So for example, if we have this as our equation, b squared minus 4ac would be negative, right? 9 minus 40, negative 31. And when it's negative, it means we have no real solutions, basically imaginary solutions. And then we also have this example. Now, if I take the discriminant here, plug it in b squared minus 4ac, it equals 0. This means we have one real solution. Last but not least, when it is positive, when it is greater than 0, we know that we have two real solutions. Next, we have the area of an equilateral triangle. Okay, so here's an equilateral triangle. All the sides are equal. They all equal s. So here is the formula. It is s squared times radical 3 divided by 4. So for example, if all the side lengths are 1, 1 squared times rad 3 over 4. If we have side lengths of 2, 2 squared, which is 4, times rad 3 over 4. And last but not least, 3, we'd have 3 squared, which is 9 rad 3 over 4. That's how you do it. Done. Next, we have a series of Pythagorean triples that are great to know and to memorize because it can help you. Not essential because you can always use Pythagorean theorem to figure out the other side lengths of a triangle, but this saves you some time, so it's pretty cool. Most common one is 3, 4, 5, and there's also multiples of 3, 4, 5 that is tested. We're going to come back to that. We also got 5, 12, 13, 7, 24, 25, and 8, 15, 17. So these are very commonly tested right triangles on the SAT. So the multiples, of course, would be 6, 8, 10, 9, 12, 15, etc., etc. Then we got multiples of 5, 12, 13, just to be mindful of. And for the 7, 24, 25, 8, 15, 17. I'm not saying to memorize all the multiples. I'm just saying keep in mind that if it's a 3, 4, 5, you might see it showing up as a 9, 12, 15, but it's still a 3, 4, 5. Next, we're going to talk about perpendicular slope, okay? So if we know that a line has a slope of m, right? Let's call it a over b. Perpendicular slope is going to be the opposite reciprocal, meaning negative b over a. And by the way, I didn't put it on here, but parallel slope means the slopes are equal. They're the same, okay? So if we had a parallel slope to a over b, it would just be a over b. So here we have an example of 2/3. That is the slope of this line. So a perpendicular slope would be negative 3/2. Another formula to be mindful of is the sum of angles of any polygon, and that is equal to n minus 2 times 180, where n is the number of sides of any polygon. So for example, if we take a triangle, 3 sides, plug and chug, we get 180, right? But that one is actually on the reference sheet, so you don't need to memorize that. Then we have a quadrilateral. We got 4 sides, 4 minus 2 times 180 is 360. And here's one more example for a pentagon. 5 minus 2 times 180 is 540 degrees. Next, we have rational functions, which are now being tested more so on the digital SAT than they were previously. And so a rational function is something like this, right? Something over something, x minus 4 over x plus 3. So what we need to know is what we can figure out from this equation right here. So I'm going to take 2 examples and we're going to look at their graphs, right? So when we look at the graph of the function, we'll notice that the x-intercept is at 4, 0, whatever is going to zero out the numerator. And there's an asymptote, vertical asymptote, at whatever zeroes out the denominator. So in this case, it's going to be x equals negative 3. Lastly, we can also quickly figure out what is the y-intercept by simply plugging in 0 for x, which gives us negative 4/3, okay? Now we'll do the same thing on the right. To find the x-intercept, what zeroes out the numerator is going to be negative 2. Where's our vertical asymptote? It's going to be at positive 5, right? X equals positive 5. And last but not least, plug in 0 for x, and we get negative 2/5 for our y-intercept. Next, we want to know all of our triangle congruence theorems, okay? All the way that we can prove triangles are congruent. And we got 5 of them. We got side, 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 show that all the sides are congruent. Triangles are congruent. We got side, angle, side. And very important, the angle has to be nested between those 2 congruent sides, right? It has to be in that specific order to prove congruency. We also got angle, side, angle. Same deal. That side has to be nested right in between those 2 congruent angles. Angle, angle, side. And last but not least, hypotenuse leg. That's only for right triangles. But if we show that the hypotenuses are equal and one pair of legs are congruent, the triangles must be totally congruent. And again, just in case you don't remember what that means, that if triangles are congruent, it means every corresponding angle is equal and every corresponding sides are equal. We also want to know our triangle similarity theorems, and there's 3 of them, okay? And proving triangles similar means that they're not congruent, but they're proportionate, okay? It's kind of like a Xerox image blown up. All the dimensions are proportionate. So we have the most commonly tested one, which is angle, angle. Show that any 2 angles in 2 triangles are congruent. They must be similar. They must be proportionate. We also have side, angle, side. Now, it's different from side, angle, side in congruency, because when we're saying side, angle, side, I'm not saying that the sides are congruent. I'm saying that we've got congruent angles and the sides around those angles are proportionate, okay? So if there's a 1:2 ratio for AC and XZ, that 1:2 ratio has to exist for AB and XY as well. Last but not least, we've got side, side, side. Again, not all the sides are congruent, but they're all proportionate. There's a consistent proportion. So one way to think about this is like that idea of a scale factor, right? ABC looks like the smaller one than XYZ here. So we could imagine that every side of ABC is half the length of XYZ, and that would show that they are indeed proportionate and similar by side, side, side. Next, we have the unit circle. So the unit circle is not essential, but it's recommended, and it can save some time if you do have a decent understanding of it and how it works. So for example, here's the unit circle. And if we are looking at what the sine of an angle represent in the unit circle, it represents the y value, okay, of these coordinates. I'm going to show you what I mean as we go through an example. Cosine is the x value, and then we have tangent of theta is equal to y over x. So what am I talking about here? So we're going to say that, for example, sine of 45 is equal to rad 2 over 2. Why? Where does that come from? Because if we look on the unit circle, that is the y value of that coordinate at 45 degrees. What about cosine of 150? That's negative rad 3 over 2. Why? Because again, look at that coordinate at 150 degrees. The x value of that coordinate is negative rad 3 over 2. Last but not least, we got tangent of 240. That's rad 3. Why is that? Because again, if we look at 240, the ratio, or negative rad 3 over 2 divided by negative 1/2, that simplifies to rad 3. That's how you do it. Now, this one is more of an algorithm really than a formula, but it is all about foiling, okay? And when I'm talking about foiling, I'm talking about foiling to binomials. So this stands for first, outer, inner, last, okay? And you can see everything popping up on the right-hand side as I'm going through those. So let's carry this out, right? So when first means we're going to multiply those first two terms, x times x, and that is going to give us x squared. Next, we're going to multiply the outer terms in red. That's going to give us negative 6 times x, negative 6x. Then we're going to multiply the inner terms, 3 times x, which gives us 3x. And then the last terms, 3 times negative 6, negative 18. We're going to combine those two terms in the middle because they're like terms, negative 6x plus 3x. And we're left with x squared minus 3x minus 18. Squaring a binomial, this is just like foiling. And a reason why I want to point this out is because it's a place where people can make a lot of silly mistakes. So for example, this is a binomial that's being squared. So you might look at it and be like, oh, cool. It's just x squared plus 9, right? You're squaring each of them. But we don't do that. We don't distribute the exponent like that. This is incorrect. When we're squaring a binomial, we're literally multiplying it against itself. So now we're back to that whole idea of foiling, right? Where we're doing the first two terms, then which is x times x, which is x squared. The outer terms, right, which is 3 times x. The inner terms, which is again 3x, and the last terms, which is 3 times 3, which is 9. Again, combining like terms, 3x plus 3x gives us 6x in the middle. There's your final answer. Done. Next, we are on to exponent rules. These are super, super important. So we're going to go through all of the critical exponent rules that you have to know on the SAT. All right. First of all, when we multiply the same bases, we add the exponents, okay? And when we have this kind of floating exponent outside of parentheses, we multiply it in, right? So that becomes x to the m times n. Over here, we have division. That is going to, with the same bases again, we're going to subtract the top minus the bottom. When we have something raised to a negative exponent, it's really going to be 1 over x to that m power. Anything raised to the 0th power is going to be 1. And anything raised to the first power is just itself. And last but not least, this is a rational exponent turning into its radical form. The top value is the power, so it's x to the m. The bottom value, the denominator, is the index. And by the way, you can take the index first and then raise it to the exponent. You can go either way. Now we're going to go through numerical examples of each. So for example, 2 squared times 2 to the 3rd. We add the exponents and we get 2 to the 5th, which is 32. Here's another example, same numbers, but now we're going to multiply those exponents and we get 2 to the 6th, which is 64. Now we have an example, again, same basis. We're going to subtract those exponents. 5 minus 3 is 4 squared, which is, of course, 16. Now we have 5 to the negative 3rd. Again, that just simply means we're dropping it to the denominator, putting a 1 on the top. 5 to the 3rd power is 125, so it's 1 over 125. Here we got anything to the 0th power. Here's 7 to the 0th is going to be 1. Anything to the first power is just itself, aka 9. And last but not least, we got 8 to the 2/3. So let's check this out. Let's break it down. It's going to be the cube root of 8 squared. What's 8 squared? It's 64. What is the cube root of 64? 4, because 4 times 4 times 4 is 64. Now, we could have also done it the other way. The cube root of 8 is 2. 2 squared is 4. So in either case, we're getting 4. Next, I want to talk about the basic protocol for solving an absolute value equation, okay? So let's say we have x minus 4 is equal to 6. We should get 2 solutions, not 1. And the way we do it is we split it into two equations. The first equation is exactly the same. We just remove the absolute value bars. The second equation is almost exactly the same, but we put a negative on that constant value outside of the absolute value. So we flip it. Now we solve these equations as is. We're going to add 4 to both sides and x equals 10. On this one, same thing, add 4 to both sides and we get x equals -2. Those are our two solutions. Done. Last but not least, we have a little thing that I want to show you on inequalities that I want to make sure you don't forget, okay? Let's say we have this inequality and you need to solve it. All right, we're going to isolate x. So we're going to add 4 to both sides, no problem. And then we got -3x is less than 9. Divide both sides by -3, okay? Standard protocol. And we've got x is greater than -3. What happened to the inequality? It flipped. It was less than, now it's greater than. Why did we do this? This is the rule to remember. Don't forget to flip the inequality symbol when dividing or multiplying both sides by a negative. So just bear that in mind. Very important. If you do forget it, you will make a mistake on this test. All right, guys, that is it for the Digital SAT Math Formula Bible. I hope you enjoyed this video. I hope you crush this test when you take it, and I wish you all the best of luck on your SAT math journey. If you like this video, make sure to click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.